Okay, welcome back. All right, so we are going to continue with the discussion of the method of characteristics, and at the end of the last session I talked about the fact that you had to make some revisions in order to deal with a boundary value problem. And let's just quickly review that. So the method of characteristics is essentially the following. We've got a PDE with some initial condition. Instead of solving that PDE, we're going to solve the characteristics equations, which are basically differential equations. We take that coefficient, we put that equal to dx dt. We take that right-hand side and we put that equal to du dt. We have the initial conditions on these differential equations here, which is that x is x0 and u is f of x0, where that's the initial condition, at t is equal to 0. So along with that, there is the characteristics diagram. So I'll put that over here for this particular problem. So we learn in this particular case that du dt is equal to u. That's what S is. So that tells us that u is equal to f of x0, the initial condition, times e to the t. And the other one, dx dt, that equals c, but that coefficient's 1. So we have that x is x0 plus t, or x0 is x minus t, and I can just simply shove that into there, and that's how we get to that solution down here. Now, just continuing with the characteristics diagram, what that says is that if I plot the space-time plane, then my characteristics here are all straight lines. X is x0 plus t. So I pick an x0, and there's my characteristic, and they all look like this. So that's what we have if we're dealing with the infinite line. Now, what we're actually after is a solution of a boundary value problem in which we don't have the infinite line, but we have a boundary. Put this in pink, that'll look best. We have a boundary here. That means that our characteristic solution that we've just found only applies to the, what's the best colour? Well, oh, it's the same as that one, dash. Oh well. So our current characteristic solution just applies over that hatched region there. That's clearly for x bigger than t. Right, there's one family of characteristics that I can build by simply taking all of the points on the positive x-axis and moving up along these lines. The issue, of course, is that there's a whole bunch of other characteristics now that instead of starting on the x-axis, they now begin on the t-axis. So we have a second family. If I now adjust this picture, that's x less than t, so that's family A, which are given by this. We have now family B, and if I choose to say that at x equals 0, t is equal to t0, then the analogue of this is family B, is going to be x is equal to t minus t0. All right, so we've actually got these two families now. So that's the issue that we face when we are dealing with a boundary value problem. But the way I've built all of this using the information of the characteristics diagram, it's fairly straightforward to see what one must do. So with the boundary condition at x is equal to 0, we emerge with a second family of characteristics they're given by this. That's what I've called V. And I'm just going to adapt everything we already have for this particular case. So we've got x is equal to t minus t0. The starting value for u that's now given by the boundary condition. And it tells us in particular that u is equal to the boundary condition, which is t e to the minus t at t is equal to t0. So we'll just put the 0 on the t there. That's how we start things off. So we need to solve du dt is equal to u with that. Okay. So that's how we must revise the problem. Right, we build a second family of characteristics that are connected to the boundary, not the initial condition. We solve, or we resolve the equation for u, which is not there, it's over here. Not here, there it is. And we apply the starting condition, and if we do that, we find that u is going to have to be t0 e to the minus t0. That's the starting condition. The solution is this sort of thing again, e to the t. And the way, let me just do my zeros better. I'm being zero challenged this morning. Okay, so the way that I've written down the solution is proportional to e to the t, and I have just introduced a suitable constant so that when t is equal to t0, I get that. So that's my solution. It is t0, but t0, if I just come back up here, that's saying that t0 is equal to t minus x. If I pop that into here, t minus x, e to the minus t0, there's another t0 there, and there's a t. So I have a t minus 2 of those, which is t minus x e to the 2x minus t. Okay, so let's just have a quick review. We've taken the PDE, we've gone to the characteristics equations, we've looked at the characteristics diagram and appreciated that we have two bits on it with different sets of characteristics. This is suitable for one of them. This is appropriate for the other one. I should bear in mind that for the specific problem that I'm dealing with here, my initial condition is 0. So it's 0. Okay, so let's just summarize all of this in a convenient way. Right, so we've got the solution down there. Let me save that momentarily. That's the statement of the problem. We've got all of these. U is going to be 0 when we have this picture. Let's get rid of all this lot. I'll save that, but I will scrub that out, so I don't care about it being a little bit smudged by the water here. It's funny. You look at this thing, and it's getting rid of this magic luminescent ink. You'd think it would be some horrible chemical, but no, it's just water. Right. So this is going to be useful because this is essentially what we'll be doing for the rest of the course. I'll leave it up in the top corner there as long as possible. I'm going to get rid of this in a second. Down here, oops, down here, I'm going to put in our summary of the characteristics diagram. This is the line x is equal to t, and down here we've got the characteristics of family A, and we've just learned, since there's no initial condition, that u is equal to 0. Up here, these are the characteristics of family B, and there we've got that u is equal to t minus x e to the 2x minus t. That's the summary of what we've got so far. Now, at this point, I'm going to draw your attention to the fact that we've previously solved this problem with Laplace transforms. What was it? Well, it was u is equal to t minus x e to the 2x minus t times a step function of t minus x. So we got that by transforming the thing in time using the Laplace transform table and so forth. And if I look at what I've just constructed, I've got these two pieces is 0 if I'm less than t, than the line, that's for t being less than x. If t is bigger than x, I'm above the line, then I get that solution. The step function takes into account the switch completely, and so I realize that I've got exactly that. So as found by the method of characteristics. Okay, so we've recovered what we already knew. And you might possibly view that this was easier than doing it that way. Okay. Right. So that's how we can deal with a boundary value problem. So we've shoved in a boundary condition. And it's clear that the way that it works is that you have to bear in mind the fact that some of the characteristics come off the t-axis rather than the x-axis. You've got the initial condition giving the starting values for the characteristics coming off the x-axis, the boundary condition giving the starting values for the characteristics coming off the t-axis. That's how it works. All right, now I'm now going to go back to the generalities of this set of equations, and I'll go back to doing things on the infinite line. Right, so I'm going to abandon the boundary conditions thing a little bit. So let's get rid of this. Now, what we said to begin with was that, okay, we're going to make up this method of characteristics, and essentially it's merely a question of changing variables. That's how it worked. We just change variables in here to get to there. And to begin with, we had c and s being constants, then we allowed them to be a function of x and t. And then I said, oh, hey, let's just do quasi-linear PDEs where c and s, those two coefficients, could also depend upon u as well as x and t, as long as they don't depend upon the derivatives of u, then we're good to go. And that leads us to these quasi-linear PDEs. And that's as far as we're going to get in this particular course. You can go further, it just gets more complicated algebraically. I should also say, by the way, that we've done it for one PDE, and there is one space variable. So as a side note, the method of characteristics can be generalized to 1 more PDEs. So you can have systems like this that do more space dimensions. And you can actually go yet further, and you can do this sort of thing for more derivatives too. The main thing is that you do it for hyperbolic PDEs. If you remember at the beginning of the course, we had a short discussion about classification. We talked about hyperbolic PDEs then. So that's really the setting for using method of characteristics here. All right, so going back to what I was saying, right, we're going to talk about one issue that comes up when you are solving this set of equations and C and S depends upon U. And the issue is that you often can't get an explicit solution. So let's do this. For a particular example, which is let's do it for this case. Right, so in other words, C is equal to U, S is equal to 0. I'm going to once more supplement this with the initial condition that I have f of x, and I'm not doing the boundary value problem anymore, as I said before. Okay, so given all of this, I just translate everything over there. I find that du dt is equal to 0. What that says is that u is fixed along the characteristic. Let's just abbreviate characteristics by that. And dx by dt is equal to c, that's u, but since u is constant along the characteristic, that's essentially just a constant now. And so I can just immediately integrate this to find that x is x0 plus ut, or x0 is x minus ut. And the starting value from here is that u is equal to f of x0. So eliminating x0 gives us this equation here. So u is f of x minus ut. So to get u, I need u. This is circular, right? And that's because this is an implicit solution. So previously this didn't happen because when we were dealing with coefficients over there that depended only on x and t, then this equation didn't have any u's in it. It was independent of that equation, so we could solve it and then we could shove the thing into there and we got an explicit solution for u immediately. Now that we've got u dependence in there, it's all got mixed up, and one of the consequences that you arrive at is that you typically will get things like this, an implicit solution. Sometimes you can solve this, so I'll solve it in a particular case. Let's do that. Let's say that this is our initial condition. So this is f of x, and it's a parabola, but only between -1 and +1. So it looks something like this. And then outside of that it's 0. So with the help of these nice colours, I'm going to just put it in. It's this, and then that. So that means that f is equal to 1 minus x squared if I am between -1 and 1, and f is 0 otherwise. That's the initial condition. Okay? Generate more space over here. Good. So with this initial condition, I can now take over, well, I've got 1 minus x squared, when I'm thinking about what's happening over that little bit. And I can now say, okay, well, I'm now going to replace the x there with the x0, which is given by that. So I've got u is equal to 1 minus x minus ut squared. And if I think about that, that's a quadratic equation for u. And I can always solve a quadratic equation. So that's what's going to happen inside this little interval here. And then outside, I've just got u is equal to 0. Right, to begin with, f is equal to 0 there and there. And if f is 0, u is 0 for all time. Right, so for the intervals in x0 that correspond to this, I'm going to solve a quadratic. There and there, I get 0. So let's just summarize that. Right, so I've got f of x0 is equal to 0 if x0 is above 1 in absolute value. That's there and there. F of x0 is 1 minus x0 squared if I'm over that interval in x0. And so solving everything, I get u is equal to 0 if x0 is less than minus 1, 0 if x0 is bigger than plus 1, and it's 1 minus x minus ut squared if I'm there. Struggling with my zeros again. There we go. That looks good. So that's the solution. So the only thing that I want to do at this point is to actually solve this for u. Okay, so that's expanding the square there. I'll put everything together. So that's u squared t squared plus 1 minus 2tu plus x squared minus 1 is 0. And I can solve that. And I'm just going to write the answer down in a convenient way, just to make it look as pretty as I can. So here it is, using my notes. 1 over t squared, 1/2 minus xt, and then there's a square root involved. Right, the t squared coefficient there has gone there and there. There's the x squared minus 1. This thing's got mixed up altogether. And we get that. Now when we solve a quadratic equation like that, you know, if you remember the formula, there's this plus or minus a square root term, and we've chosen the plus sign there. And that's guided by the fact that you've got to get the initial condition, right? So that's choosing the sign of the square root to obtain the initial condition. So that's gone on in stepping from there to there. But otherwise, that was just simply solving a quadratic equation. I used to say things like, even George Bush could do that. I'm no longer sure that the President of the United States could solve a quadratic equation. Anyway, pardon my political statements. Right, so we've got that particular solution. That's what we've got over there. We've got 0 outside that interval. There's one slight awkward thing, which is that when I write these limits, they're on x0, not x. And if I think about the fact that I've got this characteristics diagram, if I have a characteristic which starts at x0, it might go somewhere else. And so this set of divisions in x0 don't obviously correspond to the intervals that I would write down in x, which is clearly what I want to do because I want to write u as a function of x and t. So let's just quickly grapple with that. So where do we apply this, for example? So hopefully there's enough room here. Okay, so at x0 is equal to -1, that's this particular point, we actually have that f of -1 is equal to 0. Right? That means that u is equal to 0. And if u is equal to 0, that means that x is equal to x0. And similarly, at x0 is equal to +1, there, f is still 0. So we get that u is 0 again, and once more, we still have x is equal to x0. So in fact, at the end of all of this, I can simply go back to here and say, well, actually, even though these were in principle to begin with, the limits on x0, since these positions don't move as I go along the relevant characteristics, I can just simply come back here and scrub out the zeros. That's from this argument. So let's now summarize some of these details. Actually, I want to keep this. I want to draw a characteristics diagram. Actually, I don't think I need this, so I'm going to remove all of this now. Okay, all right, so just a quick summary of what we did analytically is we solved the equations, right? We put in a specific initial condition. In general, we have an implicit solution, but in this particular case, we can solve it. There's the explicit solution. There's this issue that you're given intervals because it's got this piecewise form, then the intervals are in x0. So one last bit of the puzzle there is that you have to translate the intervals in x0 to the intervals in x. Fortunately for this particular problem, the intervals don't shift. So that's where we are. Now let's draw the characteristics diagram. And this is going to be interesting and important because it's going to reveal a whole new issue that we haven't yet appreciated. Okay, so characteristics diagram. I've got this shape, and I'm only going to draw the space-time diagram, the projection of the characteristics on the xt plane. So here it is. Okay, so we've got x and t, and there's an important section of it which is from -1 to +1. Now, if I am to the left of there or to the right of there, we've got that u is equal to 0. And if u is equal to 0, x is equal to x0. So that means that the characteristics are all vertical lines. Couldn't be easier to draw. Although you'll see I just struggled. All right, so one of the key things which relates to what we were saying before is that the characteristics coming out of those points, they're vertical. And that's the reason why the intervals where we had these 3 bits of the solutions, they don't shift in space in x. So that's what the characteristics diagram looks like for the easy bits. Now for the other part, I need to draw the characteristics corresponding to that section. Now, since u is fixed on each characteristic, the characteristics are straight lines, right? So they're always straight lines even over this region. However, since u is no longer 0 but positive, in fact it goes between 0 and 1, then what's going to happen is that the slope of the characteristics now changes. Maybe it's better to write this as t is equal to x minus x0 over u, since we're drawing t against x. And so the slope of the straight lines on this picture will be 1 over u. So when u is 0, the slope is infinite. That's why they're vertical. And then it will be finite when u is no longer 0. And it will be shallowest. That means it'll be inclined most this way when u is maximum. That's when u is equal to 1 at the top. So the slope is least for x naught is equal to 0. That's when u is equal to 1. So that characteristic from there is going to be x is equal to t. All right, so there's a curve that's coming out here, which is x is equal to t. And that's the one that's most or least inclined. All of the other ones are less inclined, so they have to go from there to there as I march along from here to here, and then as I go back from there to there, they're going to steepen up again. So I'm going to put them in. Here we go. So they have to look like that. Then they're going to get less inclined. They're going to look something like this. So that's the characteristics diagram. And you'll notice there's something odd looking here. We've got the characteristics crossing over. So that's the characteristics diagram, right? Each of these lines has a value of u, and the value of u is being transported along it. All right, so u is fixed along the characteristics, right? So that information propagates along the characteristic curve, right? So it's really the information that's being transported along the characteristic. And if something like this happens, it's a complete and utter disaster. Why? Because when two characteristics cross, like at that particular point, that means that there is a point with the same value of x and t, the same time, the same space point, for which there are two values of u. So the characteristics now cross. That's a disaster. Something's gone horribly wrong, because there are now two, here there's two values for u, for each point in space and time, u is multi-valued. That means that there's no unique solution. And in this sort of business, when you're solving mathematical problems, you have to have a unique solution. Otherwise, the whole effort has been pointless. So something's gone terribly wrong. All right, well, what did go wrong? Let's have a look in a bit more detail. What we can do is we can think about plotting the solution now. What did the solution do? All right, so what happened to this particular plot? Let's draw it. So we know what the initial condition looks like. How can we draw that in a qualitative way? Well, I'm going to make a little argument, geometrical argument, to do that. If you don't like thinking about it and qualitatively drawing things, you could just slap this thing into MATLAB and it'll do it effortlessly without even thinking about it. That's always a good thing to do with characteristics diagrams. Get MATLAB to do the hard work. Okay, so this is now going to be sketching the solution. So we had this. That's our initial condition. So now I'm plotting u here as a function of time. That's t is equal to 0. Okay, well, if I think about what I was saying before, I've got all of these characteristic curves and they're transporting information. They're transporting the initial value of u, right? So all of these ones, they transport u is equal to 0, but they don't go anywhere. So u is equal to 0 stays that way everywhere along that bit and that bit of this picture. If I think about the middle point, the one at the top though, it's moving along to the right like this, it shifts that way. So at a later time, this point maybe goes, for example, there. And it's the one that goes furthest that way because this characteristic is the least inclined here. So this point shifts there. And if I take the one halfway down, for example, this one, that will be something like here. That one doesn't go quite as far, right? So this one maybe goes half, say about half of that. Maybe it goes there. And it's the same on this side. That one goes about to there. So you could just think about taking points on this initial curve and shifting them a little bit according to how far they must have got from the characteristics diagram. So these ones are not going to shift. And if I just join the dots, a favorite exercise, you're going to get something that looks like that. Drawn badly, right? You're going to get the original parabola, and it's going to have kind of slewed over to the right. Now I'll keep on going. I'll increase time again. That means the top point, which is now there, went from there to there. That's gone even further, right? And the issue is going to be that if I go too far, then what's going to happen is something like that. So as I keep on increasing t, this thing just leans over, and at some point it leans over itself and you get this overhang. Right, so this is t increasing, we get this bending over, or leaning over is probably a better word. So the curve tilts and leans over itself. There we go. I can keep on going. Right, let's just do something that's even more extreme. Right, if I keep on going, this thing's going to be way over there, like that. These points are always fixed, remember. All right, so I get this region where, if I draw a vertical line here, that value is still there. I've got that value and I've got that value, so it's triple valued. Right, there it is, it's multi-valued. There's no unique solution. That's because I've got three possible choices at that value of x at that particular time. So that's what's gone wrong. Right, the thing's tilted over, it's become multi-valued, doesn't make sense anymore. Now, let's just make some notes. So the first one is that the issue means that the solution fails. This issue is not because of the way we solve the problem. It's because of the problem itself. So the issue is not with the method of characteristics, it's with the PDE itself. So it just means that we can only continue a certain length of time, right? There's a certain window of good times down here before the characteristics have crossed. So I can only continue for some time. Let's just have a quick consideration of what that time might be. All right, so let's get rid of this characteristics diagram. Something's gone terribly wrong. Disaster. And this really has all come about because we have an implicit solution for u. And implicit solutions, implicit equations for something, in this case u, may not have a unique solution. They may have multiple solutions. So this has come about because of the implicit form of the solution that we've arrived at by solving the problem of the method of characteristics. But I stress that it's not because of the method of characteristics, it's because the problem itself, because it's nonlinear, has essentially done the dirty on us it's not a good problem. It's good for a certain while, but not for all time. It wants to create a solution that doesn't make sense. All right, so when does the issue first appear? So as I am going through this argument here, right, the thing tilted over, tilted over, tilted over. At some point, clearly, the thing tilted over and part of the solution became vertical, and then it hung itself. Right, so the division between a good solution and an overhung solution is going to be when we have a vertical cliff face. So U is vertical for the last good solution, i.e. T greater than Ts gives multi-valued solutions with du dx diverging at t is equal to Ts. So that gives us a criterion to figure out exactly when things go wrong. And we can do that because if we come back to here, we've got u as f of x minus ut. So that implies that if I differentiate it with respect to x, I've got ux as f primed. Now by the chain rule, right, and the fact that that's x0, it's f primed of x0 and then the derivative of this with respect to x, which is 1 minus t times ux. So there's a ux there and a ux there. I'll put them on the same side. That's ux is equal to, so there's an f primed of x0 divided by, and from here I get 1 plus t f primed of x0. Okay, so I'm looking for a moment when this thing diverges. Well, f primed, right, f was the initial condition, f primed is the slope of it. Right here, there's nothing wrong with the slope, that's not going to diverge. What may diverge is the fact that this denominator could vanish. Right? So diverges when this vanishes. Right, so that's going to be when t is equal to minus 1 over f primed of x0. Right, so if the slope is negative, that's a positive time. Well, okay, we've got this whole region here where we've got negative slopes. Well, so those are, in principle, will give me values of time for which this denominator vanishes. And in order to figure out when this first happens, I've just got to figure out the smallest value of that over all of the possible range of x0s here. Right, clearly, nothing's going to happen out there and there. F primed is 0 out there, so that's going to be infinite, so there's no point thinking about those bits. It's on this section, and in particular, it's going to be that part of it that is most dangerous. And what I really need is I want the smallest value of this for when things first happen. So actually I want the largest value of f prime, that's the steepest bit. Well, the steepest bit is right there. So it's going to be right at that particular point. x0 is plus 1, that's going to be the largest value of, the largest negative value of f primed, and that's going to give me the smallest positive value of the t here. That's Ts. Okay. Let's complete the calculation. Oh, I don't know why I'm keeping this. May as well get rid of that too. Right, so what have we got? Well, we've got f primed of x0 is equal to minus 2x0 over the important interval here, so the largest negative value That's obviously minus 2 at x naught is equal to 1. That's the same as x is equal to 1, remember, since that point doesn't move. Okay, so that means that Ts is equal to 1/2. So things go wrong at 1/2, and beyond that, we better just throw our hands in the air and run around screaming, because things have gone terribly wrong. Okay. Right. So at this particular point, I'm just going to direct your attention to, these are my notes, they're my lecture notes, and there's the top picture. That's done in MATLAB, that corresponded to the picture that I was trying to draw here. Okay, so there's better graphics in the notes. I don't know, but this has got the old school charm of doing it by hand on the board, the light board. Right, here we are using the light board. We are returning the power to the people. Darth Vader and the Empire must be quaking in their boots. Let's just observe a couple of other things here. This condition that I was getting down here, it depended upon f primed at the end of the day, right? Now, the initial condition that I chose had a bit where we've got a positive slope, a negative slope. The negative slope are the dangerous ones, clearly. That means actually, though, that this issue that we're facing depends on the initial condition. And if the condition doesn't have any region where the slope is negative, everything should be okay. And indeed, that's correct. Let's just see that by changing the initial condition. Actually, we can get rid of more. Let's get rid of more of this. And this. Right, so we're keeping all of that, since this is still the general solution of the initial value problem that I'm solving. I'm just changing the form of f, not changing the PDE. Made a bit of a mess there. Let's rewrite that bit, because I smudged it. I can save a bit of space while I'm doing it too. Okay, so what kind of initial condition shall we use? Well, it's got to be something that only has a positive slope, right? So it's got to start down here and go up there. So let's use something that looks sort of like a step. Right, that's our implicit solution. Okay, so e.g., let's say that f of x equals, well, what's your favorite step function? Well, there is the step function, but that's too extreme. Let's do something that's smooth at least. So my favorite smooth step-like function is the hyperbolic tangent. Okay, well, let's draw that. There's this terrible situation these days, which is that sometimes people don't know what a tangent is. Well, it's sinh over cosh. But the issue, once more, is that people don't know what that is. Sinh is e to the x minus e to the minus x over 2, and cosh is e to the x plus e to the minus x over 2. They're just composed, these hyperbolic functions are composed of exponentials. And this thing, if you plot it, it goes from -1 up to +1, and it creates a nice smooth step like that. So this is f of x. That's what it looks like. It's got positive slope everywhere. In fact, I can compute f primed. F primed of x is sech squared. That's 1 over cosh squared. right? That's something that is 0, 0, 0, comes up in a bump to 1, it goes back down to 0. So the maximum is 1. So if I do that, right, the condition for problems was that t is bigger than ts, which is the minimum over all x zeros of one over f primed of x naught, and it had to be negative, right? So here, that thing is just cosh squared, right? Of x naught with a minus sign, right? So that doesn't give us a positive time, so we don't have to worry about it. So that's what I already said before. Let's now just quickly draw what the characteristics diagram looks like. Okay, well, we've got these flat regions way off to the left and way off to the right. I should remember that x is equal to x0 plus ut. Right, so far enough off to the right, u is over here, it's 1. So I get curves that are coming out, and they're basically, at this point, they're all x is basically x0 plus t. Way off to the left, that's where u is minus 1. I get these characteristics that are going that way. They're basically x is x0 minus t. And then in between, what happens is that the slope on this picture increases, right? That's t is x minus x0 over u. U is getting bigger, the slope's getting smaller. Sorry, u is getting smaller, the slope's getting bigger. And it goes through 0 at this point. That means it goes vertical. So the characteristic at x is 0 is just the t-axis. And then these things tilt over towards the vertical as I head in. Right, so we get this set of characteristics that's doing something like that. They're all going that way, then they slowly go vertical, then they come back down to that way. Right, so we get this thing that spreads out. None of these characteristics ever cross. This calculation up there would tell you that you never get an infinite derivative of u, space derivative of u. All right, and we can just complete that picture. We can actually also put on u of x and t. So what happens now, if I think about it, was that this particular point here corresponds to something over there, and it just moves to the right, so it goes that way. The one over here moves left, so that one goes that way. The one in the middle stays where it is. The ones here, well, they all move that way a little bit. The ones here, they move that way a little bit. So if I draw this at a later time, it's just shallower. It looks something like this. And then if I keep on going, it gets yet shallower. So it looks something like that. So going this way corresponds to increasing t. Right, and that's just thinking about what happens at sample points. Right, that point there could correspond to, say, this characteristic here. And this one there, that could correspond to this one. Right, so that one and that one, these points and those points. Right, and they're spreading out, so the u has to spread out because u is transported along the characteristics. That's the information that's being carried along. So that's what it looks like. And here's some notation, some terminology. So cases that sharpen up to head to multivaluedness, to multivalued solution. That's called shock steepening. The cases that spread out Sometimes you see those called rarefactions. Things are getting more rarefied, getting more spread out. Okay. All right. Now, one last thing is that if I'd have switched this around, so if it was a step down, so had I put a minus sign there, I would have had negative slopes. Right? That means that that would have now been plus cosh squared. The smallest value of that, the smallest value of cosh is 1. So I would get a value of a sensible value for this TS here, which will be 1. And that would mean that this thing is now stepped down. That means that it's steepening up. And at some point, a bit of it goes vertical. Thereafter, things become multi-valued. So switching around the step would lead me to this case. The way I've got it, I've got that case. So the issue clearly depends upon the initial condition. Okay, so I'm going to stop and we'll continue with a development of everything where we actually end up being able to deal with these situations where things look like they ought to become multi-valued. So that's next. Let's stop for the